Today, we're diving into Penn Bioengineering. But we're not just looking at it as a school department, we're looking at it as a complete ecosystem, one that's built from the ground up for one specific purpose: innovation.
And we're going to explore some really wild stories. I mean, think about this for a second. How do you take a fungus, one that was rumored to be part of a pharaoh's curse, the kind that supposedly killed archaeologists, and then turn it into a potential treatment for leukemia? Sounds impossible, right?
Or what about this? How do you tell the body's own immune system, hey, stop attacking yourself, especially after something as traumatic as a heart attack? This is a huge problem that affects millions of people every single year.
Well, the answer to both of these incredible questions starts right here. It's not about one person or one lucky discovery. It's about an entire environment, a whole ecosystem that's designed to take those little sparks of genius and nurture them until they become world-changing solutions.
So let's get into how this ecosystem actually works. It all starts with fueling the research itself, giving brilliant faculty that initial push they need to go after some really high-risk but potentially high-reward ideas.
So this number you see, 500,000, represents a massive, massive challenge. After someone has a heart attack, their own immune system can go into overdrive, and that can lead to heart failure. It's a contributing cause in 500,000 deaths in the US alone, every year. It's exactly the kind of problem a researcher like Dr. Noor Momin is determined to solve.
And check out this timeline. This shows just how quickly things can move in the right environment. An initial seed grant from one of Penn's centers let Dr. Momin gather the critical early data she needed. And with that data in hand, she landed a major award from the American Heart Association in less than a year. In the world of research, that pace is, in her own words, exceptionally fast.
And look, you don't have to take my word for it. Dr. Momin said it herself. That seed grant was the key. It was crucial, and it essentially jump-started everything. It's the perfect example of how a relatively small investment at the very beginning can unlock huge progress. That's the ecosystem doing its job.
This idea of finding opportunity everywhere brings us back to that whole Pharaoh's curse thing. The fungus Aspergillus flavus has this really dark history, seriously. It's been linked to the mysterious deaths of scientists opening ancient tombs. But fast forward to today, and Penn engineers have figured out how to take molecules from this deadly fungus, tweak them, and create a compound that actually shows promise in killing leukemia cells. It's just a mind-blowing story of innovation coming from the absolute last place you'd expect.
Now, this ecosystem isn't just about developing new treatments. It's also about cracking our body's most ancient and fundamental codes. Building the instruction manual for the next wave of medical breakthroughs. A big focus for researchers is this thing called the complement system. Okay, so get this. It's an ancient part of our immune defenses. We're talking 500 million years old. Think of it like this internal security system that puts tags on anything it doesn't recognize, viruses, bacteria, but also sometimes medical devices or even new drugs.
So the billion-dollar question has always been, when does this system decide to launch a full-blown attack? Well, researchers at Penn figured it out. It's not just about if the tags are there, it's about their density. If the tags are spread out, the immune response just kind of fizzles out. But if they get packed together and cross a critical threshold, the attack ignites like wildfire. By cracking this mathematical rule, they're learning how to basically control the immune system's on-off switch.
So you have this incredible foundation of knowledge and this supportive environment. Well, it doesn't just produce amazing research papers. It produces leaders. The ecosystem is also a powerful training ground for the next generation of scientists who are going to change the world. Just look at the story of Dr. Kelsey Swingle. As a PhD student, she didn't just do good work in a lab. She basically pioneered a whole new field, using mRNA technology to go after preeclampsia, a really dangerous pregnancy complication that has no effective treatment. Her work was so groundbreaking that she did something almost unheard of. She jumped directly from finishing her PhD to landing a tenure-track faculty job at a top university.
Her mentor, Professor Michael Mitchell, calls her the complete scholar. And he's not just talking about her research skills. He's talking about her ability to teach, to lead, He says that she is absolutely ready for that huge leap, and that's just a massive vote of confidence in the quality of the training she got.
And Kelsey is not an exception. Just look at this list of the 2025 Pollack Award winners. It shows you the insane breadth of the research being done by grad students. We're talking injectable cartilage repair, mapping the genome for Alzheimer's, new pathways for cancer, and of course, Kelsey's own work on preeclampsia. It's a snapshot of excellence across the board.
I mean, the success from just this past year is pretty staggering. Students brought home a whole slew of honors. We've got 4 prestigious NSF fellowships, a highly competitive Schmidt Science Fellowship, multiple awards from the Association of Immunologists. The list goes on. This doesn't happen by accident. It's what happens when you build an ecosystem designed to help people thrive.
And this culture of innovation, it goes all the way down to the undergraduate level. The senior design program challenges students to, as one of their instructors put it, take a plan that sounds like science fiction and actually build a real high-quality biomedical device.
For instance, you have Team Reflex. They built a system that reads a stroke patient's brain signals. Literally, it detects their intent to move a limb, and then it uses that signal to trigger electrical stimulation. It's basically helping to rewire that broken brain-body connection to speed up recovery.
Then there's Team Prism Optics. They looked at a massive global problem. More than 1 billion people don't have access to basic vision care. So what did they do? They built a low-cost, automated device that lets people figure out their own eyeglass prescription, no doctor needed.
And finally, Team Prime created a device to help detect sepsis earlier. Sepsis is incredibly deadly, and catching it early is everything. Their device automates the monitoring of a key vital sign, which can free up nurses and catch problems faster in a chaotic hospital setting where every single second counts.
So when you put all of this together, the seed money for faculty, the deep fundamental discoveries, the training of these incredible young leaders, you get something much bigger than just the sum of its parts. You get a multiplier effect.
And the center's director, Daniel Hammer, explains this perfectly using Kelsey Swingle's story. He points out that when Kelsey starts her own lab, she's going to train her own students who will then go on to do great things. Her career has this incredible multiplicative effect that spreads the influence of this place far beyond its own walls. That's the real endgame.
From that small seed grant that jumpstarts a career, to an undergraduate project that could save thousands of lives, to a graduate student who becomes a leader in her field, this is exactly what an ecosystem of innovation looks like when it's firing on all cylinders.
It's a really powerful model for turning raw scientific curiosity into real-world, tangible impact. And it just leaves you with one big, exciting question. With an ecosystem this powerful, what on earth will they engineer next?